Hello everyone. Today we are going to see the second chapter, that is laser action. Students, in the previous lecture we have seen about the interaction of the light with matter, the population density, Boltzmann distribution law, and the Einstein coefficients and the Einstein's relations. Students, today we are going to see about the metastable state, the population inversion, and the condition for the large stimulated emission. Students, in the first chapter we have seen about the atomic energy levels, and in the atomic energy levels we have seen the two states of the energy levels, which are the ground state energy level and second one is the excited state energy levels. But now today we are going to see about the metastable state, and what do you mean by the metastable state, and what is the role of the metastable state in the lasing action. The higher energy state of an atom of the molecule, in which the atoms or the molecule stays for a usually longer duration of the time, is called the metastable state. Now see here, this is the energy level diagrams, in which we can see here the lower energy state, which is known as the ground state energy level, and the upper energy state, which is known as the excited energy level. And in between these two states there is one of the state which is known as the metastable state. We know that when the atom goes from the ground state energy level to the excited state energy level, now then in the excited state energy level the atom will stay for a very short duration of the time, and it may be in the nanosecond. But when it goes to the lower energy level, which is known as the metastable state, and in this metastable state the atom will be stay for usually longer duration of the time, and it may be in the range of millisecond to the microsecond, and which is known as the metastable state. So in case of the lasing action, the metastable state having the very vital role. Students, for the generation of the laser, any device must satisfy the two important conditions. The first is the formation of the population inversion. The population inversion occurs for an energy transition when more of the atoms are in the excited state than are in the ground state. Okay. And second is the process of the stimulated emission. So in case of the every type of the laser, it must satisfy these two conditions. That means the first one is the population inversion and second one is the stimulated emission. Now see here, now I want to tell you the different components of the lasers. Now see here, this is the basic block diagram of the laser, and it consists of the different component such as, now this is the active medium. Now there are the two mirrors are used which are known as the reflectors. Now see here, this is the total reflector, and at the another end this is the partial reflector. So it forms the laser cavity. And third one is the pumping systems. So you have to remember the basic components of the any type of the lasers, such as the active medium, the laser cavity, and the pumping system. Now then we are going to see in details about the population inversion. What do you mean by the population inversion and why it is important in the lasing action? In the first chapter we have seen at the thermal equilibrium the photon absorption and the emission process takes place in an atomic systems. And we know that under the thermal equilibrium the number of the transitions from E2 to the E1 must be equal to the number of the transition from E1 to the E2. That is, the net change in the number of any excited atom is zero. But however, the laser operations requires obtaining the stimulated emission. So for obtaining the stimulated emission, there is need of the population inversion. The non-equilibrium state where the population of the upper energy level N2 is more than the population of the lower energy level N1, and it is known as the state of the population inversion. Now see here in this diagram we can see this is the normal population in which the number of the atoms in the ground state energy level are greater than the number of the atoms in the excited state. But at the non-equilibrium state, here the number of the atoms in the upper energy state, that is excited state, are greater than the number of the atoms in the ground state energy. So we can say that the state of the population inversion is referred to as the negative temperature state. That means the state of the population inversion is a non-equilibrium state. So in case of the lasing action, the system should be satisfied. The system, in that system, there should be a population inversion. The population inversion is an artificial situation that is established by generating a large number of the atoms in the higher energy state than that of the lower energy state. So with the help of the different pumping methods, we can achieve the population inversion in any type of the laser systems. That means the N2 should be greater than the N1, that is the population in the excited state, that is upper energy level N2, it should be greater than the population of the atoms in the lower energy state, that is the ground state, and this condition is known as the population inversion. So remember, what is the basic condition required for the population, what is the basic conditions required for the lasing action, and that is the population inversion condition. Now then we are going to see about the condition of the large stimulated emission. So the second condition required for the lasing action is the stimulated emission. In the previous lecture or in the first lecture we have seen about what we mean by the stimulated emission. Now lasing is the process which leads the emission of the stimulated photons due to the transition of the atoms from the metastable state to the ground state after achieving the population inversion. Now here we can see, in case of that the any laser system or the laser device, there is the formation of the population inversion in between the ground state and the metastable state. And the stimulated emission will be achieved when the transition from the metastable, when the transition of that atoms from the metastable state to the ground state. We know that in absorption, when the one incident photon comes in and the no photon comes out, that means when the incident photons incident on the atoms which are in the ground state, now then it absorbs the energy of the incident photons and it goes to the excited state. So there is no any photons will be come out during that the process. But in a stimulated emission process, when the one incident photons comes in and the two photons will be the come out. That means during the transition of the atoms from the metastable state to the ground state, and when the incident photons interacts with the atoms during this transition, now that times when the one incident photons interacts with the atoms during the transition, that times the two photons will be come out. So now in this way, when the population inversion exists between the upper and the lower levels among the atomic system, then it is possible to realize the amplified stimulated emission, and the stimulated emission has the same frequency and the phase as the incident radiation. So we can say that during the stimulated emission, there is the amplification of the photons, and the emitted photons which having the same frequency and phase of that the incident radiation, that is the incident photon. So now in this figure we can see that when the one incident photons interacts with the atoms during the transitions from the metastable state to the ground state, that times it emits the two photons which are propagating along the same directions, which having the same frequency and the phase of these incident photons. So now in this way, the large number of the photons will be get emitted along the same direction of the incident photons, and we can say that there is the amplification of the photons in the stimulated emission process. So the stimulated emission is generated under the special conditions which is stated by the Einstein. So now we are going to see about the condition of the large stimulated emissions. Now in the previous chapter we have obtained the Einstein coefficient relations. Now that is the ratio of the two transitions, that is the A to 1 to the ratio of the A to 1 to the B to 1, that is equal to the 8 pi h nu cube into the mu cube divided by the c cube. Now here h is the Planck's constant, the nu is the frequency of the incident radiation, mu is the refractive index of the medium, and c is the velocity. Now here we are going to consider the two conditions. The first one is that now let the ratio of the stimulated transition, by taking the ratio of the stimulated transition to the spontaneous transitions. Now let us take R is equal to be the ratio of the stimulated transition to the spontaneous transitions. So we can write here the R8 is equal to be the dN1 by the dt, that is the rate of change of the population of the energy level N1, which is in the simulated condition, to the rate of change of the population N1 dN1 to the dt, which is in the spontaneous process. Now, but we know that we have already obtained these relations, that is the rate of the transition of the stimulated emission, it is equal to the B21 into the rho nu into the N2, and the rate of the transition of the spontaneous emission, it is equal to the A21 into N2. Now here the B21 and A21 are the Einstein's coefficients during the stimulated emissions process and the spontaneous emission process. Now then, by substituting the values of the RST and the RSP, that is the rate of the transition emission and the rate of the spontaneous emission, so we get R8 is equal to the B21 into the rho nu into N2 divided by the A21 into the N2. So we get here the R8 is equal to the B21 divided by the A21 into the rho of nu. But we know that the density of the incident radiation, it is equal to be the, that is the rho nu, it is equal to the 8 pi h nu cube into the mu cube divided by the c cube divided by the e raised to e2 minus e1 divided by the kt minus 1. Now we have already obtained the relation of the density of the incident radiations in the first chapter. Therefore, by substituting the value of the rho nu in the equation number 1, now then the equation number 1 becomes the R8 is equal to the B21 divided by the A21 into the 8 pi h nu cube into the mu cube divided by the c cube divided by the e raised to e2 minus e1 divided by the kt minus 1. Now then, by substituting the value of the ratio of these two coefficients A21 divided by the B21, now we can write here the R8 is equal to the 8 pi h nu cube into the mu cube divided by the c cube into the 8 pi h nu cube into the mu cube divided by the c cube divided by the e raised to e2 minus e1 by k2 minus 1. So by cancelling these two factors, we get R it is equal to the 1 divided by the e raised to h nu by kt minus 1. Now if we assume the frequency of the incident radiation, if we consider the yellow light, then the nu it is equal to the 5 into 10 raised to 14 Hertz at the temperature 2000 degree Kelvin. Now then, if we substitute this value, then we get the ratio h nu by kt is 11.99 by using the value of the Planck's constant and the Boltzmann constant k. Now then, if we substitute the value of the h nu divided by the kt, we get R it is equal to be the 1 divided by the V raised to 11 minus 99 minus 1. It is equal to be the 6 into 10 raised to minus 6 here. That is, the ratio of the stimulated transition to the spontaneous transition is equal to the 6 into 10 raised to minus 6. Now if we arrange this, so we get in terms of the spontaneous transition. So the spontaneous transition is equal to the stimulated transition into the 6 into 10 raised to 6. That means this shows that in the optical region, the spontaneous transition dominates over the stimulated emission. But the basic condition required for the latching action, latching action is the stimulated emission should be greater. Therefore, for the large number of the stimulated emission, the light field density, that is the rho nu present within the material, is required to be enhanced. That means if the density of the incident radiation will be increases, now then the stimulated emissions will also be increases. If the spontaneous emission equal to the stimulated emission, then the ratio of the stimulated emission to the spontaneous emission becomes, that is R is equal to the 1. So now remember here, in case of that system, if the spontaneous emission, that is the rate of the spontaneous emission, when becomes equal to the rate of the stimulated emission, then the ratio of the stimulated emission to the spontaneous emission becomes 1/2. So that is R is equal to the 1. Now then the second conditions is the ratio of the stimulated transition. If we take the ratio of the stimulated transition to the absorption transition, that is R is equal to be the ratio of the stimulated transition to the absorption transition, that is equal to the RST by R absorption. So the R stimulation divided by the R absorption. So we can write here in terms of the transition, that is the rate of the transitions of the atomic level. So we get here the R is equal to the dN1 by dt during the stimulated transition divided by the dN2 by dt during the absorption transitions. Now we have already obtained the relations of the stimulated transitions and the absorption transition. That are, the stimulated transition is equal to the B21 rho of nu into the N2, and the absorption transition is equal to the B12 into the rho of nu into the N1. Now here the B21 and B12 are the Einstein's coefficient during the absorption and the stimulated transitions here. By substituting these values, the values of the stimulated transition and the rate of the absorption transition, so we get R is equal to the B21 rho of nu into the N2 divided by the B12 rho of nu into the N1. Now, as we know that these two Einstein coefficients, that is B12 is equal to, are equal, that is B12 is equal to the B21. Therefore, we get the ratio of the stimulated transition to the ratio of the stimulated transition to the absorption transitions becomes equal to be the R, it is equal to the N2 divided by the N1. Therefore, at the equilibrium conditions, we can write this ratio is less than 1. Therefore, we can write here the N2 divided by the N1 is less than the 1. So here, this shows that at the thermodynamic equilibrium, the absorption transition overwhelm the stimulated transitions. That means in this case also, the absorption transition dominates the stimulated transitions. But for the latching action, it needs the stimulated transitions should be greater than the absorption transition. Therefore, to achieve the more stimulated emission, the population N2 of the excited state should be made larger than the population N1 of the lower energy state. That is, the N2 should be greater than the N1. Then and then the population inversion will occur or will achieve in between the metastable state and the ground state, and that population inversion can be obtained with the help of some external systems, and which are known as the pumping system. So in next lecture we will see about the different types of the pumping methods which are useful for achieving the population inversion. So the students, the two conditions to be satisfied for the stimulated emission to overwhelm the spontaneous emission, that are, the one is the population of the excited level should be greater than that at the lower energy level. That is, the N2 should be greater than the N1. And second one is that the radiation density in the medium should be very large. When these two conditions will be satisfied by the any laser system or the laser device, now then it generates the laser, or there will be the lasing action, and it will emit the radiations, and that radiations are known as the laser. So you have to remember about what is the requirement of the lasing action and how to enhance the stimulated emissions. Now we are going to see here, we are going to take the two problems which are dependent on this topic. The first one is calculate the temperature at which the rate of the spontaneous emission is equal to the rate of the stimulated emission for the wavelength of the beam is 5500 angstrom. Now first write down the given things. Now here in this problem, the wavelength is given, that is lambda, it is equal to the 500 angstrom unit. Convert it into the meter, that is 500 into 10 to minus 10 meter. Now here the condition is given, that is the spontaneous emission is equal to the rate of the stimulated emission, and we know that this ratio becomes equal to the half. Now h is the Planck's constant, k is the Boltzmann's constant. Now then you have to calculate here the temperature. Now but before that you have to calculate here the frequency. We know that the c is equal to be the nu lambda. Now then by substituting the value of the c and the lambda, we get the frequency, and it is equal to be the 5.4 into 10 raised to 14 hertz here. Now then by using this formula, that is the ratio of the stimulated emission to the ratio of the spontaneous emission to the stimulated emission, that is R is equal to be 1 divided by the e raised to h nu by kt minus 1. We know that according to the given condition it is equal to the 1/2. Now then by rearranging these terms, so the e raised to h nu by kt minus 1, it is equal to the 2. By taking the natural log on both sides, so we get the h nu by kt is equal to be the log of 2. Now then by substituting these values of the h, now then the h, by substituting the values of the h nu and the k, now we get the t, it is equal to be the t, it is equal to be here the 3,78,143 degree Kelvin. So now in this way we can solve the problems by using the formula, that is R is equal to the 1 divided by the A raised to h nu by kt minus 1. Now then we are going to take the second problem. Calculate the wavelength of the beam at which the rate of the spontaneous emission is equal to the rate of the stimulated emission for the temperature the 300 degree Kelvin. So now in this case here, now first write down the given things here. The T it is equal to 300 degree Kelvin. The condition is given, so the R it is equal to the 1/2 by taking the values of the Planck's constant and the Boltzmann's constant. You have to calculate here this lambda. Now then by using the same formula, R it is equal to the 1 divided by the e raised to h nu by kt minus 1. Now then the R is equal to the 1/2 here. Now by substituting, by rearranging these terms here, so by taking the logarithm natural log on both sides, so we get h nu by kt is equal to the log of 2. Now then by substituting the values of the hc and the kt, now then we get the value of that, the lambda, and the lambda it is equal to the 69.3 into 10 to the minus 6 meter, or we can write here the lambda it is equal to, or the wavelength of the radiation it is equal to the 69.3 micrometers. So here, now remember here how to solve the problems. So by in case of that, if the condition is given, that is the rate of spontaneous emission is equal to the rate of the stimulated emission, and by using this formula we can calculate the wavelength also and the temperature also. So the students, now in this lecture we have seen about what is by the metastable state, what is by the population inversion, and what is the role of the population inversion, and the last one is the condition. We have obtained the conditions for the large stimulated emission. So remember about these three, that is the what is by the metastable state, what is by the population inversion, and what is the conditions for the large stimulated emission. So thank you.